Good morning. In this presentation, we'll discuss about multiple regression. There are several explanatory variables in multiple regressions. There are two possible approaches to obtaining improved fits in regressions. So they are all to examine a scatter plot of the residuals for nonlinear patterns and then to make appropriate modifications to the regression equations. The second approach is much more straightforward. Add more explanatory variables to the regression equations. For example, if we take Bendrix manufacturing which was discussed already, because of scatter plots indicate that both explanatory variables are also related to overhead. It makes sense to try including both in the regression equations. The linear fit should be improved. This is the objective. So when include several explanatory variables in the regression equation, it can be moved into the realism of multiple regressions. And there are characteristics of multiple regressions. First one is graphically no longer fitting a line to a set of points. So if there are exactly two explanatory variables, you can assume fitting a plan to the data in three-dimensional space. So there is one dimension for different variable and one for each of the two explanatory variables. Although a flat plane passing through a swarm of points, it is difficult to graph this onto a two-dimensional screen. And if there are more than two explanatory variables, you can only imagine the regression plane drawing in four or more dimensions is impossible. The regression equation is still estimated by the least square method. The least square method we already discussed to minimize the error. That is minimizing the sum of squared residuals. It is definitely not practical to implement this method by hand. A statistical software package such as star tool is required. So nowadays the researchers always using software package to discuss different variables. So simple regression is actually a special case of multiple regression. That is, an equation with a single explanatory variable can be considered multiple regression equations. So even for multiple regression also, the simple regression is a special case. This explains why it is possible to use star tools multiple regression procedure for simple regression. There is a slope term for each explanatory variable in the equations. See, the interpretation of these slope term is somewhat different than simple regressions. When you compare this simple and multiple regressions, the interpretation of these slope term is somewhat different. The standard error of estimate and R-square summary measures are almost exactly the same as in simple regression. See here, interpretation of regression coefficients. Here you can see if y is a different variable and x1 through xk are the explanatory variables, then a typical multiple regression equation will be formed like this. Here you can take general multiple regression equations. A predicted y equal to a plus b1 x1 plus b2 x2 plus so and so bk xk is given. Here a is the predicted value when x becomes 0. If we put x equal to 0, then the predicted value will be y. A. So there will be no change over here. And when you do any changes in the x, that will try to change the y predicted value. So where the same thing is given for here, where a is again the y intercept and the b1 through bk are the slope. Here b1, b2 is also bk and will be called as slope coefficients, and a and b are all will be called as regression coefficients. The intercept is expected value of y when all of the x's equal 0. Each slope coefficient is the expected change in y when this particular x increases by 1 unit and the other x is in the equation remain constant. I told you. Okay. Here, if you do any changes in x even by a single 1 unit, that will try to affect the y value. Remaining all can be a constant. So these estimates of the b's depend on which other x's are included in the regression equations. See the start tools I told you. Here you can regression type can be selected over here, and there are options like variables, parameters, graph, and options. So according to our requirements, we can choose the variable. For example, we have given two variables I and d. Here we have taken I variable 2 and d we have taken 1. Even if you want to change the parameter, by selecting this option you will be able to change the parameters, and you can choose the choose the graph, which type of graph you want. Okay. So there the data set is also available. By selecting this, what type of data you are going to take for the analysis, you can choose it over here also. So by using this start tool, if you do analysis on the variables, the output will be like this. So this is the start tool multiple regression output for matrix examples. Here you can see multiple regression for overhead data. So there you have different options like multiple R square, adjusted R square, and standard deviation estimation, and rows are ignored. For everything the values are given separately. The other one is the ANOVA, the statistical analysis. Here you have degrees of freedom, sum of square, and mean of squares, f value, and phi values. For the everything, explained values given separately, and unexplained values are given separately for each and everything. So regression table, finally, the regression table can be created. Here they are given constant, machine hours, and production runs. So everything will be formatted in the form of matrix. So table format. So it is a multiple regression interpretation of standard error of estimate and R squares. Adjusted R square is the measure that adjusts R square for the number of explanatory variables in the equation. So when you form an equation, there how many variables you are going to bring, explanatory variables. By adjusting the R values, okay, it can be measured. It is used primarily to monitor whether extra explanatory variables really belongs in the equations or not. And the standard error estimate is essentially the standard deviation of residuals, but it is now given by equations this. Here the formula for a standard error of estimate in multiple regression is given over here, where n is the number of observations and k is the number of explanatory variables in these equations. So the same value we plotted a scatter plot. So here we have taken two variables like overhead and points. So everything is scattered over here. The graphical indication of this high correlation can be seen in one of the requested scatter plot. The plot of fitted values versus observed value of overhead. These scatter plots appear in this figure. The regression equations and gave perfect predictions of all the points in this plot will be 45. If you see this, okay, the perfect will be in 45. See here, it will be like that. The multiple regression correlation and scatter plots. When there are multiple potential x's for the regression on y, it is useful to calculate correlations and the scatter plot of y versus x. But that correlation and the scatter plots are of two variables only, so they do not necessarily tell the whole story. Sometimes, as in this overhead example, a multiple regression can turn out quite differently than might be expected from correlations and scatter plot alone. So specifically, the R square value for the multiple regression can be considerably smaller or larger than might be expected. So what is the expected value? Compared with this expected value, this R2 value will be either smaller or larger. So the estimated coefficients of any explanatory variable typically depends on which other explanatory variables are included in the equations. Here R square, adjusted R square and standard error of estimate. So sometimes the regression equation is built by successively adding explanatory variables to an equation. So why we need to give much importance to R over here? So to estimate the standard error. As more variables are added, it is mathematical fact that R square must increase. It cannot decrease. So when you have more and more variables, automatically the error will also be increased. However, the standard error of estimate can increase and the adjusted R can decrease. So because of that, we are going for adjusted R. So each signaling that the extra variables are not useful and should probably be omitted from the equation. In fact, the purpose of adjusted R square is to monitor whether the equation is getting better or worse or more variables are added. This is the last point important. The purpose of adjusted R square is to monitor whether the equation is getting better or worse or as more variables are added. When you add more variables, what is the status of the R? Okay, so that must be very important. Thank you.